One application we might have for understanding the different gas processes is in using what we call a heat engine. Now, a heat engine is just some device that's capable of taking energy in the form of thermal energy, something that's at a warm temperature, and cooling that object off and changing that thermal energy into some more useful kind of energy, usually kinetic energy. So we might think about using a gas to expand in some container and drive some part of that container forward or away from the part where the gas is, which is how the engine in your car works. So we have, it can be a pretty complicated process overall, but we can imagine fairly simple steps here. We have some system here, some gas with our pistons, with whatever else is involved here, and then going into that, we have energy from in the form of heat, and this will be at a temperature that we'll call TH, the hot temperature, and we're going to have some heat flowing into this system, and the amount we'll call that QH, the amount of heat that comes from our hot temperature stuff, matter, whatever that thing is, and goes into our system, into our engine here. Now, our engine also is, they typically run pretty warm then as a result of all this heat that goes in, and so our engine is also going to be in contact with some air or other parts of the car or whatever the machinery is we're talking about, and so there's some colder area that we have in contact here as well that's at some temperature that we call TC, the cold temperature, and we have some heat that's flowing from our engine, which is going to be warmer, to this air or the other bits of metal, or again, whatever matter is around this engine. The amount of heat that goes there, we'll call that QC. Now, we have a certain amount of heat entering this system and a certain amount of heat leaving this system, and we design these things so that more heat enters than leaves, but we keep our system at a roughly constant temperature by having our system do work on the outside world. And it turns out that the amount of work we can do is going to be equal to the amount of heat energy we put in minus the amount of heat energy we put out. So that's the amount of work we can do in these processes. Now, if our goal is to create an efficient engine, then ultimately what we want to do is have most of this energy, most of this heat that goes into our system turn into work. And so that's going to happen by minimizing this amount of heat that leaves our system, that goes out as exhaust or goes out as warming up the rest of the car. And so we're trying to minimize this value. Now, if you've ever stuck your hand by the tailpipe of your car or lifted the hood of your car when it's been running for a little while and felt around in the engine block, really bad idea, by the way, you understand that the amount of heat that's coming out of that system is not small. It's not minimized. In fact, it turns out that of this energy we put in the form of heat, about 90% of it for a typical car leaves that engine as heat, and only about 10% of it leaves as work done on these pistons used to move the car forward. So our cars then are really inefficient. They don't take they don't use much of this energy that's put in to do the job that we're asking them to do work here. And so the efficiency of this situation, the efficiency is just a measurement of, it's going to be usually written as a percentage or just a part. We could have it as a decimal, but it's the percentage of energy that reaches the form that we want it to, that reaches the desired form. And so in this case, if we want to find efficiency, the total energy that we're putting into this thing is given by QH. The amount that makes it to this form work we call W. And so our efficiency is going to be work, the amount of energy in the form that we want it to be in, divided by QH, which is the total energy that we put into this thing. And like I said, this is often written as a percent, so you might multiply it by 100 to make it look like a percent. I noticed that on the AP equation sheet, they just have it written this way. So we understand that 0.15 is the same as 15%, if that's what we come out with as an answer. So we don't really need to include that in the equation. It's also worth noting here that we might think of the work or the heat as positive or negative depending on the system that we're using, the convention that we're using. So we just put absolute value signs around here to indicate that efficiency is always going to be a positive number here. So this is the actual efficiency of a heat engine, is the work that comes out of it divided by the total energy that we put into it. Now, as we decrease this value of QC, our efficiency would increase. And so ultimately what we would love to have, which we'll never have, which we can't have, is we would like QC to go to 0. So then work is exactly equal to the energy we put into it if QC is 0. So then efficiency would be equal to QH over QH, which is 100% efficient. Hey, that'd be awesome, 100% efficient vehicles. The problem here is that if we want to put out no heat, if we want the net heat output into this cold reservoir to be 0, the only way that's going to happen is if we're putting out exhaust at a temperature of absolute 0. Like I said, if you felt the exhaust on your car, you know that we're nowhere near absolute 0 on that, nor could we be. If we're putting out exhaust or we're putting out heat in matter in the form of some temperature that's significantly below the surrounding temperature, heat doesn't flow that direction. It doesn't flow from colder things to warmer things. And so we have this limitation really based on the temperature of the surroundings on what we can do for efficiency. So if we had a perfectly efficient engine here, heat engine, as efficient as we can get it, I should say, not perfectly efficient because that means 100%. The most efficient engine we could get, like I said, it depends on the temperatures of the engine here. It depends on the temperature of this thermal reservoir here, the hot parts. Not so much on this temperature, that kind of factors out of our equation. And it depends on the temperature of the cooler surroundings. And so it turns out that we can calculate the efficiency maximum. The maximum possible efficiency is given by this equation. It's written as the temperature of our hot reservoir minus the temperature of our cold reservoir divided by, again, the temperature of the hot reservoir. So we can see if our surroundings were at a temperature of 0 Kelvin, then our maximum possible efficiency would be equal to TH over TH, which is 100%. But since our surroundings for these cars or whatever else we're talking about for engines is at some temperature above absolute 0, then even if we make really, really nice, slick, streamlined cars with well lubricated, almost frictionless, totally frictionless even engines, even in that situation, this idealized, perfect, impossible situation, we still can't get to an efficiency of 100% because we're not operating these in an environment that's at a temperature of absolute 0. So this equation can tell us at the temperatures that we're dealing with, so the temperature of the gasoline once it's ignited in the piston, and the temperature of the air surrounding the car, or the ambient temperature, what we can get for our maximum efficiency. Now, that's assuming, again, that we have no energy lost in other forms. We have no friction that's causing extra heat to be moved around, or we're not generating noise with these engines, and we're not radiating energy from inside here. So all those things are happening all the time, and so they reduce our efficiency from this maximum value even further. So the maximum value is less than 100%. The true value given by this equation, that's going to be even less than this one.